For over a century, Einstein's field equations have accurately predicted the macroscopic behavior of gravity. From the orbits of planets to the collision of black holes, general relativity remains an empirical triumph. The mathematical engine driving this success is the metric tensor. It maps the curvature of space and time, dictating the exact geodesic paths that matter and light must follow. Yet the theory operates with a known physical blind spot. It assumes the existence of spacetime geometry, but it provides no definition of the physical substrate that actually creates it. We know exactly how the geometry behaves, but we do not know what state of matter gives rise to it. Dynamic vacuum field theory, or DVFT, was developed by Satish Thorway to resolve this exact problem. It provides a mathematical framework to identify the physical vacuum state. Gravity is the measurable behavior of an emergent material medium, a physical vacuum whose state determines the geometry of our world. If you study physics at the graduate level, you will encounter a strict objection to this approach. A single scalar field cannot reproduce the full tensorial structure of general relativity. This objection is entirely correct. It is mathematically impossible to algebraically redefine a single local scalar field into an unconstrained massless spin-2 gravitational field. Historically, direct scalar gravity theories fell into exactly this trap. By forcing a direct identity between a scalar field and gravity, it produced models with conformal limits, an inability to generate transverse traceless shear, and zero accurate light deflection. DVFT resolves this by separating the microstate from the macro response. The complex scalar field defines the local state of the physical vacuum. The spacetime metric is simply the macroscopic constitutive response tensor of that medium. The metric emerges from the vacuum state in the exact same way acoustic metrics emerge from the pressure and density of condensed matter systems. To construct this emergent metric, DVFT describes the vacuum using a complex order parameter, defined by an amplitude variable and a phase variable. The amplitude variable, denoted by ρ, governs the inertial response of the vacuum. It defines the physical stiffness and inertial density as a local region. This normalized amplitude dictates time dilation, mapping directly onto the gravitational lapse function, controlling the metric's temporal component. The natural logarithm of this amplitude defines the effective gravitational potential, yielding exact vectors that draw matter into an amplitude well. While the amplitude perfectly constructs Newtonian gravity and accurate time dilation, modifying only the time-time component of a metric cannot account for spatial curvature. Any theory stopping up the temporal lapse fails solar system tests involving photons. Proper light bending relies equally on the metric's spatial dimensions. We can isolate this requirement by examining the isotropic weak field line element, which splits the temporal and spatial geometric components into distinct terms. The critical variable controlling the spatial metric is the parameterized post-Newtonian parameter, gamma. It measures the spatial curvature response, also known as gravitational slip. To correctly recover the Einsteinian lensing observed in our solar system, a highly coherent vacuum state must strictly enforce a gamma value equal to 1. DVFT collapses entirely if it cannot derive this required spatial curvature. To do so, the theory relies on the remaining half of its scalar field, the vacuum phase. The phase field, denoted by theta, contributes tensorial structure through its spatial gradients. DVFT introduces a constitutive ansatz bridging the scalar vacuum state and rank 2 geometry. First, a normalized vacuum phase flow vector establishes directional coherence across the state. Next, a spatial projector creates an orthogonal spatial geometry entirely distinct from the phase flow. Finally, the core rank 2 phase tensor injects anisotropic stress, angular momentum, and topological winding directly into the spatial dimensions of the metric. The tensorial structure required for spatial curvature emerges strictly from bilinear measurement responses and anisotropic gradient stress within the vacuum. It requires no impossible mathematical redefinitions. This leaves one final theoretical hurdle. Gravitational waves exhibit transverse traceless spin-2 polarizations. If the underlying field is scalar, how can these specific polarizations exist? The solution requires distinguishing the fundamental properties of a field from the collective responses of a medium. In a highly coherent, stiff vacuum regime, compressional scalar modes become heavy. The medium strongly resists longitudinal compression. However, shear-type collective modes remain exceptionally light. These transverse distortions propagate freely through the medium, carrying helicity ±2. Under DVFT, the tensor waves observed by LIGO are the macroscopic acoustic shear modes of a profoundly stiff dynamic vacuum. For this effective metric to dictate reality, matter and light must couple universally to it. In DVFT, the equivalence principle emerges naturally because all matter propagates through the same vacuum response metric. By proving this universal coupling, DVFT recontextualizes the classic Einstein-Hilbert action. It is no longer the fundamental starting point of gravity. Instead, it is an effective action that emerges under specific local limits. The vacuum must possess high coherence, low gradients, and linear phase kinetic invariance. When these strict physical conditions are met, higher-order nonlinear correction terms vanish. The resulting mathematics perfectly mirror Einstein's field equations. General relativity is not replaced. It is explicitly derived as the rigid, localized mathematical limit of a deeper physical state. But the utility of DVFT lies in what happens when this GR limit breaks. In deep space environments characterized by extreme low acceleration, the nonlinear phase response of the vacuum begins to dominate. Analytical, this optical image of a spiral galaxy highlights one such deep field deviation. Under DVFT, nonlinear phase responses actively alter galactic rotation curves in these outer edges, producing the observed velocities without requiring particular dark matter. This capture of a gravitational lens shows extreme photon bending. In cosmic voids where coherence drops, the spatial curvature parameter diverges from 1. This gravitational slip creates distinct, modified weak lensing signatures. The nonlinear phase equations also predict a void gravity hill. An amplitude-enhanced region of the vacuum acts as a topographical peak, actively repelling local matter and producing negative convergence course. By mapping the microphysical substrate of spacetime, DVFT provides falsifiable physical mechanisms for the phenomena we currently assign to the dark sector.